Good morning, students. Today is day 2 of digital learning. Today we will look at equivalent fractions and ratios. In math, a proportion are two equal fractions or ratios. A key word today is a proportion. In math, two equal fractions or ratios form a proportion. A proportion is simply a statement that two ratios or relationships are equal. One of the ways you have done this in the past is you've used the giant 1, you've used images, and today we will also start to look at what is a cross product. Our learning target today: I will recognize equivalent fractions and determine if two fractions or ratios are equivalent. What is a ratio? Where do we see them? You might have noticed an old television show where the screen was 4 in length for every 3 in height, which looks very different than a ratio of a widescreen or normal television that's 16 by 9. As you look at these figures up above, you might notice that they don't look the same or similar, and it's because the ratio of their sides, height to width, is not the same. Maybe you even have an anamorphic widescreen, which has a ratio of 2.3 in length for every 1 in height. In this example over here, you're going to notice what is the ratio of circles to triangles. The ratio of circles to triangles is there are 4 circles for every 3 triangles. What about the ratio of triangles to circles? Well, in this case, there are 3 triangles for every 4 circles. It's a relationship. So in this picture down here, you'll notice that there are 8 circles compared to 6 triangles, and this relationship is the same as for every 4 circles, there are 3 triangles. What are the forms of a ratio? How do we write them? Just don't forget, order matters. In this example right here, you'll notice there are 2 circles and 3 triangles. So if we are comparing circles to triangles, the ratio is for every 2 circles, there are 3 triangles. Or with a ratio using a colon, for every 2 circles, there are 3 squares. Obviously not triangles. In the last example, we would use words, or the third way, and for every 2 circles, there are 3 squares. So does order matter? Yes, order matters. So what's a proportion, and how do we build it? Well, if we look at the example, for every 1 happy face, there are 2 green happy faces. And we can rename fractions by multiplying by the giant 1. So when we multiply fractions, we multiply across numerators and then denominators. So for every 2, there are 4. This example, again, if we reversed it, would simplify to for every 1, there are 2. Let's do one together. How can you make an equivalent ratio? What giant 1s could you multiply by? Were you thinking 2 halves, 3 thirds, 4 fourths, or even a million? Millionths. So we can rename this one by multiplying by 2 halves, and you would get 4/6, an equivalent ratio. Or you could even multiply it by 4 fourths, a giant 1, and you would get 8/12, another equivalent ratio. You try one. How many equivalent ratios can you make? Did you get 6/10? Did you get 9/15? 12/20? All four of these ratios are equivalent. If we talk about simplifying a ratio, we would go back down to 3/5 because the greatest common factor of 3 and 5 is 1. Are they equivalent? How can you tell? Well, obviously we could go back to saying we can look at it like a scale factor and say, well, 1 is being multiplied by 2, so we would have to multiply the bottom by 2. Again, this is the giant 1 method. However, when we get to the next example, you might not know what you're multiplying by. So there's another way. In this case, we're going to use what's called a cross product. So going back to our first example, we're going to use something in mathematics that's kind of cool. The first cross product here would be 2 multiplied by 2, which is 4. Going the other way, this cross product would be 1 times 4, which is also 4. Because the cross product 2 times 2 is equal to the other cross product of 1 times 4, 4 does equal 4, therefore we can say the ratios are equivalent. So then we can ask, are the ratios equivalent? Is 2/3 equivalent to 3/4? Can you just add 1 to 2 and 1 to 3 and get 4? I'm not sure if that will work. So let's try it again. The cross product here would be 3 times 3, which is equal to 9. The cross product here, 2 times 4, would be equal to 8. Does 3 times 3 equal 2 times 4? Or does 9 equal 8? No, they are not equal. Therefore, the fractions are not equal. What about the final example? Is 3/5 equal to 5/7? Do you know how to find the cross products? The cross products are 5 times 5, which is 25, which is equal to 3 times 7, or 21. And we ask, does 25 equal 21? The answer is no, so these fractions are not equal. Okay, so your brain's hurting. What do students do when they get it wrong? Some students think that 2/3 is equivalent to 3/4. Why might they say that? Can you think how they would have gotten that? See, this student might have added 1. This is called additive thinking. It's not a good time for that. The process works. Unfortunately, 2/3 is not equal to 3/4. And we would prove that by saying 3/4 we would say the cross product is 3 times 3, which is 9, and 2 times 4, which is 8. Since 8 does not equal 9, these fractions are not equal. Other students might think that 2/3 is equivalent to 6/4. What might they be thinking? Why can they not be equal? Is 2/3 more or less than 1? Is 6/4 more or less than 1? 2/3 is less than 1, and 6/4 is greater than 1, because 4/4 is 1. Therefore, they cannot be equal. Again, we can also prove that with cross products. 2/3, 6/4, the cross products would be 18, and 8. Since 8 does not equal 18, the ratios are not equal. The end. That's all, folks. Next step will be to use this when we have a missing number in a pair of equivalent ratios. So look forward to that the next time we see each other.